guys. Good afternoon, guys. All right, looks like you are all here. Very good. All meaning three of you. All right. So, so tomorrow's lab is going to be an easy lab in a sense, and the theory is even easier or smaller. So we'll be finishing very quickly. So the lab you are doing is called saponification. Saponification, a very interesting, unusual word. Saponification. By the way, am I sharing the screen? Maybe not. Hold on, let me share the screen. All right, yes, now you can see me. Right, see me? All right, so you will be doing saponification, and saponification means soap making. Some of you may or may not know. Saponification actual meaning is soap making. So how is it relating to the lab you will be doing? In a sense, you will be making a soap. In a sense, you will not be making a soap. You will be doing the chemistry of soap making. Although I had asked Konga last time to have the chemical that actually makes a soap, I still have doubt whether he has acquired that chemicals. So if you did, that's fantastic. If not, you will learn the method at least. Now, in early days, this is actually soap making chemistry is probably one of the oldest chemistry that was used even before the birth of Christ in the Middle East, usually in Babylonian civilization, etc. And how they made soap was making from animal fat. So animal fat they will treat with ash, just the ash from burning, I don't know, straw or some any other fiber, things like that. So how does it actually work? So the reason it works, so let me tell you give you the reverse thing first. That is going to help understand what is soap molecule is, and at the same time why soap is made from the fat molecule. So let me give you a fat molecule, understanding of the fat molecule itself, especially the triglyceride. Triglyceride molecule is the animal fat. Many of you are familiar with this. You have elderly people in your family, and they often have triglyceride issues. Doctors often say that, etc. So what is a triglyceride? Triglyceride is an ester of glycerin. That's why it is called triglyceride. Why tri and why glyceride? So let me show you. The glycerin molecule is actually a, what is it called? A triol, which is like this. 1, 2, 3 propane triol is glycerol. This is the same glycerol that you find in drugstores as glycerin. It used to be sold even in Home Depot and such places too. I'm not sure if they sell nowadays. So glycerin and glycerol is the same thing. This 1, 2, 3 triol. Now, if I write this structure, let's say in this manner, here I am writing the same thing with an E and then O each one. Each one, that is the same 1, 2, 3 propane triol. Imagine an ester of this. You have learned esterification just in the last class. The carboxylic acid and alcohol together make ester. Recall that discussion here? I'm sorry, hold on. Let me take this out. So a carboxylic acid, if I write like this, here is a carboxylic acid, and R, it's not 2 carbon, I mean to write many carbons. How many carbons? many carbons. I'm just without counting, I'm just writing like this. What I am indicating here is a carbon number somewhere between C14 and let's say C20, or it can be C14 and C18 in this range. It could be 18 or 20. So if you have a carboxylic acid, something like this with alcohol together, imagine the corresponding ester that would make 3 moles of that together based on what you learned in the last class, esterification. And I'm not really indicating Fischer esterification. I'm just trying to show the ester between alcohol and carboxylic acid. So here is that, and here is that many carbons. Here is that carbonyl group and many carbons. As you see, so alcohol part of this esterification is the triol, and 3 moles of this long chain carboxylic acid, if you imagine that being the carboxylic acid component, together make an ester of the glycerin. And that is what is triglyceride. This is your triglyceride. Triglyceride, which is animal fat. Okay, that is animal fat. We all have triglyceride in our body. If it is too much, it is bad. If it is too little, it's not good. We need some. It's a very interesting balance we need in our body. We say cholesterol bad, but you need cholesterol. Without cholesterol, you cannot live. Cholesterol is an extremely important thing in for our body function, for all the hormones to work. It is an extremely important component. But if it is slight imbalance, the LDL versus HDL ratio is a little bit twisted, then it's a problem. Otherwise, the high number is not the problem. That's why let's say in Italian people have extremely high cholesterol, but they're not unhealthy because they have good ratio. Their HDL is pretty high. So usually, okay, I'm not going to go too much into medical discussion, although it is related to that I could, but if you have question, I will ask you later. I will answer later. So this is our triglyceride molecule. But if you recall, this reaction I'm showing as if you are making an ester, right? Here you have an alcohol, which happens to be a triol, right? Because it has 3 hydroxyl groups, so it is actually triol. And this is a carboxylic acid, and this is our ester. And this ester of long chain carboxylic acid is a fat molecule, an animal fat, which is called triglyceride. And if you recall last class, I had also mentioned the opposite reaction is hydrolysis, meaning a triglyceride, if you hydrolyze, then you will just get the opposite, just the opposite thing, right? The reverse reaction is hydrolysis. Reverse reaction is hydrolysis of ester, right? Which in this case, this ester is the fat molecule. So we are planning on hydrolyzing an ester, and that ester is not necessarily a triglyceride, but it will be an ester that has this long hydrocarbon chain on the carboxylate part of the acyl group part will have long hydrocarbon chain. If that is the case, then that will be an ester hydrolysis. So let me write in the reverse reaction in this sense, hydrolysis of ester. And this time I'm not using triglyceride, I'm using a simple mono functional ester. But the principle is the same, chemistry is the same. So in this case, we are deliberately using an ester in which on the carboxylate side we have a long hydrocarbon chain. And then on this side you have some kind of relatively smaller size from the alcohol side. As I said, this side, when this carbon side is very large, and I will indicate large again one more time, which can be C16 through C22, such ester, which is also a fat molecule, just not triglyceride. This is also a fat molecule, by the way. Basically, a long hydrocarbon chain on the carboxylate side, and ester with long hydrocarbon chain on the carbonyl side is a fat molecule. This is a fat molecule. Okay, and when it is triglyceride, you have three such ester functional group. That is triglyceride, that is animal fat. But it is not triglyceride. Then this fat molecule has regular fat, which is present in animal, also has that. In fact, some oils will also have that. Okay? Now, if we hydrolyze this, in this particular case, this hydrolysis, we are deliberately doing a base hydrolysis, not the acid hydrolysis. And the reason for that, if you do base hydrolysis, only then you are going to get soap molecule. And that is why it is called saponification. So hydrolysis, when you are doing with a base, and the reaction is very straightforward nucleophilic acyl substitution reaction that we have learned in organic 2, which is this. So here a base meaning hydroxide, which can be sodium hydroxide or potassium hydroxide, right? That is going to be a simple nucleophilic acyl substitution reaction, nucleophilic acyl substitution reaction, and that mechanism is extremely simple. Hydroxyl group attacks the carbonyl group, and carbonyl functional group carboxyl double bond breaks, the result of which, again, I'm not counting, I'm just making zigzag to show the reaction. O becomes O minus, and here you have OH is your nucleophile, OR is the part of the ester. In a nucleophilic acyl substitution reaction mechanism, as you know, the carbonyl group reforms because the leaving group is present. OR is a leaving group. So leaving group leaves. And our incoming group was this nucleophile, was the hydroxyl group, that is this. Reaction is done in this base medium, but base is hydroxide, but when hydroxyl group is attached to carbonyl group, then it becomes an organic functional group, right? It's not hydroxide, hydroxy like hydroxy group. So what is the result of this? If you do complete this reaction mechanism, so this part is here, you have this, I'm just still making zigzag, and carbonyl is back, and here is your OH, plus you have OR minus, that was the leaving group. Right? That is our nucleophilic acyl substitution mechanism, as simple as this. Now, here is something interesting. You're doing the reaction in a basic medium, right? Sodium hydroxide is a pretty strong base. The product looks like an acid, like this is an acid. That is a strange thing to think about. How can you have an acid in a base? Acid and base reaction is fast. Because I use the term in the lecture, acid and base reaction is fast and furious. Their reaction is much faster. They are not going to be watching around. Base immediately reacts with the acid. Meaning, this you see as a carboxylic acid that is forming initially, that is not going to stay as such. Hydroxide will immediately react with that. But this time, reaction is acid-base reaction. Before, hydroxide was the nucleophile. Look at this. Here is, you understand the organic chemistry well. Just few seconds ago, we are seeing hydroxide as a nucleophile, having the ester on the carbonyl group. And now, the base is reacting with the acid. That is going to be acid-base reaction. That is not nucleophilic electrophilic reaction. That will be acid-base reaction. Meaning this base, oops, let me use the other color. This base is going to pick up the proton of the acid, right? Because it's protic acid. So Bronsted acid, Bronsted base. Therefore, that is going to be simply acid-base reaction. And that has to occur, oops, that has to occur because acid cannot stay in a base. They will immediately react together. And that reaction is just acid-base reaction makes a salt. Simple reaction you learned in Gen Chem. Acid-base reaction is salt. So I'm putting this zigzag and showing here you have this and here you have O minus. You know, this part of the mechanism, you know, base picks up this proton, O becomes O minus, and that is this O minus. Your base is sodium hydroxide, even though you do not write, I wrote once. You have the sodium ion, and the sodium ion is the cation of this carboxylate ion. This molecule is a salt, sodium carboxylate. Only thing is, when this carbon chain is so large between C16 and 22, C22, then this molecule is a soap molecule. Okay? Then it is a soap. So, hold on, my phone is ringing. I think people are calling to vote for them. Okay. Sorry, I forgot to mute. Now I muted it. I have already voted. I voted early voting. I voted on by mail. So my voting is done. I did my civic responsibility. Anyhow, so here is pay attention. This carboxylic salt of the original carboxylic acid, when the carbon chain is between 16 and 22, then it acts like a soap molecule. And that is indeed a soap molecule. Okay, you have learned this how soap molecule function. I may have a picture. Hold on, let me get a picture. I did not bring it here. I may have it. Somewhere here. Yeah, I do. Okay, here is a picture of a soap molecule. So look at this. If you look at the picture, let's say the second one is the blue, the one I am moving my cursor. The blue end is actually that carboxylate anion part. And the long chain hydrocarbon chain is the inward part. Hydrocarbon is hydrophobic. They don't like water, but they like each other because they are hydrophobic. So they are clustered together in this manner. All the hydrophobic ends, which is the oily part, doesn't like water. They aggregate together, keeping this hydrophilic part outside. Hydrophilic is the anionic part. They stick outside. So how soap molecule works? How do you get your soap clean your clothing? Imagine the first one. I think in the middle I indicated this a grease molecule in the middle. So, or you can see in the third picture, in the center is a dust particle or a greasy, fatty dirt that you have or sweat, all these dirty things. They are actually hydrophobic also. So they get dissolved by these hydrophobic ends of individual soap molecules. So remember, each soap molecule is one blue ball with this long tail. Many of them together, they dissolve out one dirt molecule or dirt mass inside them, having all the hydrophilic part outside. And that can be washed away because outside being anionic part that attracts water and it dissolves away and your dirt is gone. That's how you clean your thing. Here are some of the oily substance or oils that are used to make soap or can be used to make soaps. Here's a list of different oils. Coconut oil. It has carbon number 12, 14, 16, 18, etc. at various proportions. Olive oil has, you see, huge numbers. 78% is carbon 18, but it is unsaturated. Okay. Canola oil has 8%, etc., etc. So anyhow, so this is a soap molecule. So indirectly, we are making a soap molecule only because you are making a carboxylate salt of sodium by means of hydrolyzing an ester. So basically, you will be given an ester molecule. This is an ester. Your ester may not be such large hydrocarbon chain ester. If it is, then it will indeed look like a soap molecule, which may not be the case. Your ester molecule may be somewhat smaller, okay? Most likely to be smaller. But still you are going to be getting the hydrolysis product and the carboxylate salt. Another part of this is this carboxylate ion that has formed, that because it is aqueous solution in water, that is going to become protonated and it becomes your alcohol. So ideally, the alcohol can be distilled off. There is a good chance your alcohol can be a 4-carbon alcohol, which is kind of butanol, that can be distilled off as an azeotrope and forms an azeotropic mixture. So even though you are not going to get a soap, which there is a possibility of a large ester molecule that will result in a soap molecule. If not, if our inventory is not that, then you might be getting something that is small size and you have 5 carbon group on the alkyl group. That's not really a soap because that is going to give you a carboxylate which is sodium acetate. That is far from a soap. To be a soap, this has to be really, really large, as I showed you above. So you are not really, may not be making any real soap, but you'll be making a method of soap making, which is base hydrolysis of ester, also called base promoted hydrolysis of ester. So in the case when the carboxylate is large, then it is a soap molecule. Then it is a soap molecule. So that is all about this lab. It's not intense at all. Relatively straightforward and short lab. So you should be able to finish quickly enough. If you are able to separate the alcohol, you will be able to analyze the alcohol using FTIR, because IR gives you a very strong signal for alcohol, right? So if you are able to separate them, separation may be a little bit difficult because carboxylate salt, depending on how many carbons it is, I'm not entirely sure. But supposedly we'll be able to distill off the alcohol. If you do, you're going to get a peak for the hydroxyl peak in the FTIR. So you can analyze alcohol using FTIR. Now you cannot use TLC on these. TLC is totally useless because TLC, try to understand the again the chemistry aspect. I had something in the question. Also in your midterm, in a TLC you have the stationary phase is silica, which is a highly ionic substance, highly polar. Your product here is a carboxylate salt and alcohol. Both of them are polar, meaning none of them are going to move in a TLC plane. So that is obsolete. Okay, you can analyze that. So whatever you get, if you see two different layers, you separate them and you take an FTIR of that. That's going to be all as far as analysis. Yeah, not much. All right, so just supposedly it should be a fun lab of this nature, and that's about it. Yeah, no, it should be easy and fun lab. All right, guys, any question? Anastasia, Danny, Jinho, Oscar. All right, sounds good. All right, Sam. Yeah, it is. It should be straightforward. By the way, how did the last low? I checked. It did good. Everybody separated ester. It smelled like banana. Some of them were pear or apple. They're what is it called? It's a small structure variation, actually only one carbon variation. Smell can change from pear to apple, apple to banana. The difference in their ester is not much, small difference in their alkyl group, by the way. So you should be able to figure it in the NMR. So don't make a quick assumption. Make sure your multiplicities are matching with the NMR multiplicity that you find in the NMR spectrum. All right, sounds good. All right, so good luck. Have a nice lab tomorrow. I'll try to stop by. All right. Good. Okay. Okay. Bye bye. You're welcome. Bye bye. Have a good night.